Hi, everybody. It's Miss Rose. We're going to continue on our theme of studying right triangles from last week. And week 24 is going to be about special right triangles. So I'm going to teach you about the first special type of right triangle, which are called 45, 45, 90 triangles. And then in the next video, Mr. Millington's going to teach you about the other type, which are called 30, 60, 90 triangles. All right, let's take a look at this first example. I have a square, and we're totally prepared to do this problem based on what we learned about the Pythagorean theorem last week. It says squares have a side length of 8. So side length 8, and then remember all four sides in a square are congruent to each other. And also remember that squares have right angles. So I can use the Pythagorean theorem on this problem because if I highlight this, the two sides of the square and the diagonal make a right triangle. So I'm going to take the two legs, the 8 and the 8, and then the hypotenuse, I'm going to call that x, and I'm going to substitute it into the Pythagorean theorem. Leg squared plus leg squared equals hypotenuse squared. 8 squared is 64. 64 plus 64 is 128. And then remember, the last step of the Pythagorean theorem is to take the square root. And darn, 128 is not a perfect square. So what we're going to do is use what we learned last week and try to simplify that radical. So hopefully you still have your list of perfect squares handy so that you don't have to keep remaking this list every time. And we're going to look for the biggest perfect square that goes evenly into 128. So 128 divided by 100, nope, decimal. 128 divided by 81, nope, decimal. 128 divided by 64, ding, 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 that's the winner. 64 times 2 is 128. And then if you remember what we did last week, 64 is perfect, so you can square root it and it gets to go out of the house. So square root of 64 is 8. And then square root of 2, that's messy, so it has to stay in the house. So if you have a square and the side lengths are 8 and 8, the diagonal is 8 root 2. So this is actually an example of a 45, 45, 90 triangle because the diagonal of a square cuts the right angles in half. So these angles here are 45 and 45. So let's try another example and then check and see if you can see a pattern that we can use to help us solve more of these types of problems in the future. So let's do same type of problem. So the two sides are going to be congruent again. Let's do 9 this time, 9 and 9. So you can think of these 45, 45, 90 triangles as half of a square, or you can think of them like isosceles right triangles. All right, Pythagorean theorem time. The two legs are 9 and 9, 9 squared and 9 squared. The hypotenuse is x. 81 plus 81 is 162, and then the last step is always we square root both sides. And darn, that's not a perfect square either, so we still need to go back to the list of orange perfect square numbers that I made up above. So 162 divided by 100, decimal, but 162 divided by 81, we already found the winner. 81 times 2 is 162. So square root of 81, that's perfect. It gets to go out. Square root of 2, that's messy. It has to stay in. All right, do you notice anything? Look at the first example that we did. 8, 8, 8 root 2. Look at the second example that we did. 9, 9, 9 root 2. This actually makes sense because 45, 45, 90 triangles are all similar to each other because their angles all match up. So there's a pattern that we can use every time. So starting now, let's be lazy. Let's use a shortcut. I love a good shortcut. Don't do the Pythagorean theorem from now on when you see these isosceles right triangles. Use our shortcut instead. So I'm going to show you how that works one more time just to be clear on what the shortcut is. So every time we had two legs that were always the same number because the triangle was isosceles, and then the hypotenuse always ended up being that number, root 2. So let's take a couple notes on this. Let's jot these down as some good examples to have written down to do future problems. So here's our general case. The legs are x and x. So the hypotenuse will be whatever that x number is, root 2. And that is how these work. So what if one of the legs, for example, was 7? Well, then the other leg is 7 because the triangle's isosceles. And then what would the hypotenuse be? 7, 7, 7 root 2. All right, let me switch colors. Let's do another example. What if the hypotenuse was 15 root 2? Pause for a second and figure out what the legs would be. Well, if the hypotenuse is 15 root 2, we can just divide out that root 2 and the two legs would be 15 and 15. All right, I have one more example for you, but this one's a little bit trickier. Let me switch colors one more time. What if the hypotenuse was just a plain 12? Now what would the legs be? So see if you can pause and think about this one for a second. All right, let me tell you the two most common mistakes that I see. Mistake number 1 is people tell me that the two legs will be 12 root 2, but that's not possible because the hypotenuse has to be the longest side. So it has to be something shorter than 12. The other mistake is people tell me that there's 6 and 6, but then where did the root 2 go? All of a sudden now we can't have triangles where all 3 sides work out to be nice whole numbers. So maybe you figured out that the two legs would be 6 root 2. Because if you have 6 root 2, that's 6 times 2, which is 12. If you are satisfied with this is a little shortcut, realizing, oh, I just take half of 12 and put a root 2 on it, then you can stop the video right here and start getting to work using this pattern. If you want to know why and you want to see more algebra about why those legs turn out to be 6 root 2, then keep watching and I'll show you. All right, for those of you who are still here, thanks for sticking with me. Let's take a look at the middle green example first. When the hypotenuse was 15 root 2, you just had to divide out the root 2 to see what the legs were. And those obviously cancel and just leave you with 15. But in the orange example, if you have 12 and you divide out root 2, now all of a sudden nothing cancels. So we have to do a little bit more algebra. So we actually need to think back about, first off, what operations we're allowed to do to keep fractions equivalent to what we started with. And then second of all, we need to think about what we learned last week about square roots. So when it comes to fractions, the only thing you're allowed to do is to multiply the top and the bottom by the same number. So that really you're just multiplying the fraction by 1 and you're keeping it equivalent to what you started with. So what we learned last week is that if you multiply a square root by itself, the square and the square root undo each other and you're just left with what's inside. So what we're going to do is we're going to multiply the top and the bottom of this fraction by root 2. And what happens on the bottom is we have root 2 times root 2, which is like root 2 squared, which is just 2. Or you could look at it like root 2 times root 2 is root 4, and the square root of 4 is 2. On the top, we have 12 times root 2, which is 12 root 2. And then the last step we can do is we can divide and simplify. 12 divided by 2 is 6. So 12 root 2 divided by 2 is 6 root 2. And that's why those are the lengths of the legs. So feel free for the practice to use the shortcut. You can just take half of the hypotenuse and put a root 2 on it. Or feel free to do this algebra. It's called rationalizing the denominator, and it's something that you'll probably see more of in Algebra 2. All right, let's try that practice and use these patterns, and good luck. Bye.